In Module 1, we're going to give you an overview of the SDN landscape. We're going to talk about overview and terminology of SDN, as well as what problem we're solving with SDN in general, as well as ACI. And we'll talk about the logical model overview and the concrete model overview of the ACI fabric. So SDN and overlay networking primer. So there's a couple industry trends that are affecting what has been a traditional data center of VMware and Nexus switches and compute, storage, network, all that. The first one is the advent of cloud services or cloud computing. Now, NIST defines cloud computing as a cloud computing platform as one being self-service. So that's a pretty big contrast to how we've been doing things in IT for the past 20 years or even more, where we, if you want a resource like a virtual machine or a server or disk space or some sort of network turned up, you would open up a ticket. For Amazon and Google and Cloud Foundry and Salesforce and all those, it's all self-service. So when users are used to self-service services, it's hard to go back to tickets. So users and consumers of IT resources are demanding self-service and immediate spin-up. Another one is the type of workloads that we're seeing in our data centers. For the past 7-8 years at least, it's been primarily VMware with vCenter. So virtualization workloads, but we're seeing a more heterogeneous workload, things like big data, Hadoop and so forth, that are very different network profiles than what we've been used to in the traditional Nexus 7K, 5K, 2K stack. Plus the advent of DevOps, the concept of network as code or applications as code, where we're keeping the state of a device separate from that device. For example, with a server, rather than going into a server and installing, or a virtual machine even, and installing things by hand, we are defining some sort of manifest or cookbook, and we're instantiating it from that. Also the concept of immutable infrastructure or composable infrastructure. And then finally, we have the concept of SDN itself, things like OpenFlow and network virtualization and programmability. All of these are affecting the data center as we see it today. So what is SDN? Some people say still don't know. SDN is kind of like what happened to the term cloud for the past couple of years. Larry Ellison had a pretty epic rant on the term cloud in 2009. And it was a fair one at the time because it was a term, it was mostly a marketing term, and it was thrown against a lot of things, and it was hard to define. And that's where we are right now with software-defined networking. Now, in 2010, NIST, the National Institute of Standards and Technology, part of the U.S. Department of Commerce, came up with a widely accepted definition of cloud computing, one that had several aspects to it. We still don't have that right now for software-defined networking. So, of course, SDN stands for software-defined networking, and there's really kind of three, reasonable people can disagree on this, but there's really kind of three tenets of SDN right now. The first one is a centralized controller of the control plane and data plane, something like OpenFlow. So when the first iterations of what we call now software-defined networking came out, it was a research project, I think, in Stanford. Martin Casado, Martin Casado, who created OpenFlow, and his team. They also formed Nicira, which got bought by VMware, which is now the NSX product. But they came up with the concept of a network operating system. So it was a controller sitting outside of your network devices, your routers or switches, or really sometimes there's not much of a difference between them, but sat outside of those devices, took a look at the network, and then told ports how to forward traffic very explicitly through the OpenFlow protocol. So the idea of a centralized controller rather than a distributed control system like we have with Spanning Tree and Mac Learning and ISIS and OSPF and so forth. Next, we have the concept of network virtualization, so virtual networks that we can set up and tear down on demand. Also, things like virtual firewalls, load balancers, and security devices that can be inserted and consumed. And then finally, a heavy emphasis on programmability. Being able to programmatically define our network forwarding, define our networks, everything from just using some sort of something like a REST API to define an SVI, all the way to defining an entire network profile through JSON, XML, REST APIs, and the like. So that's really kind of encompasses at least most of what we know as SDN in the market today. So one of the aspects of software-defined networking is the concept of network overlays. So we're going to talk about this concept a lot in this class. We have the concept of the overlay network and the underlay network. The underlay network is typically will be a fast L3 non-blocking ECMP fabric. So we have our spines up here, and we have our leafs down here. Now, one of the things that people will disagree on is how do you just say leaf? Is it leafs as in with an F, or is it leaves as in trees of a leaf? I've seen it more as leafs, so that's what we're going to use in this class. So spines and leafs, non-blocking ECMP fabric, sometimes referred to as a CLOS fabric or a layer 3 fabric or a leaf spine. Anyway, this network is the underlay. It's a very simple network. It's a very static network. It's our infrastructure network, and it doesn't change very often. On the other hand, we have our overlay networks. So we can create these virtual networks that ride on top of our underlay. And these networks are highly dynamic. We can do multi-tenancy with them. So we can have some networks belong to Coke and others belong to Pepsi. We can spin them up and tear them down on demand. We can allow users and consumers of IT resources, developers and administrators, access to spin these up and tear them down and make changes to them. Whereas the underlay network is going to be something that only the infrastructure team touches. And the primary technology used to build these overlay networks is VXLAN, and to kind of a much lesser extent these days is NVGRE. Most of the time it's VXLAN that's being used now. There's a couple others like I think OV3 and a few others have been created, but pretty much it's a VXLAN game these days, and that's what the back end of ACI is based on. So we take this encapsulated traffic, we take normal Ethernet frames, we encapsulate them into these VXLAN packets, and we route them over a network. So Cisco ACI, let's talk about the overview of the technology as well as the terminology that you'll be hearing a lot in this class. So Cisco ACI stands for Application-Centric Infrastructure, and the overall idea behind it is we're going to build networking around applications rather than around networking constructs. So if you take a look at your traditional application, many applications would consider a 3-tier, or this could be a microservice. So a microservice is when we take a large monolithic application and then we break it into very discrete functions. For example, Netflix.com may look like a large single unified site, but it's actually a collection of about 700 to 800 microservices. And one microservice might be a small stack, a web server, app server, database server, whatever. And its entire purpose is to show you the last 5 things you watch. That's all it does. So the web server front end's an application logic. The application logic will query a database, either a dedicated database to that setup, or a shared database on another service, or consuming another service. Anyway, it might be that we have a large monolithic application, a more traditional application, or we might have a microservice. Either way, we're going to typically have more than one tier. And sort of the traditional tiering that we've been seeing that we've seen traditionally is the web server tier, the application server tier, and the database server tier. Now, this is by no means the only way that you'll see applications deployed, but this is a good starting point and a good way to show the basic fundamentals. And of course, we have the outside network, so that typically will represent the internet. An outside network can be represented by a small network, a small subnet, or it can be represented by, oftentimes it'll be 0/0. So this will be every route, sort of a default route. Although the concepts are slightly different, in which we'll get into a little bit in more detail. In between each layer, we have protections. We have filtering that we can put in place. We can also put in services such as firewalls and load balancers, external services. We can rely on internal ASIC-based firewalling, or we can rely on an external firewall such as Palo Alto or an ASA. And then we have QoS and other SLA type things that we can put in place. So when we think about an application, that's what, at least what the application developers are thinking about. They're thinking about the outside world. They're thinking about their tiers of their applications, how they connect, and how they communicate. So in ACI, we are going to be able to instantiate this policy. We're going to be able to define the policy of these application tiers. We'll put it into something called an application network profile, and then be able to instantiate that onto the ACI fabric, relying on an integrated VXLAN overlay. So sort of the secret sauce, the magic behind ACI is the concept of the network profile, the application network profile, or ANP as you'll sometimes hear it referred to. So this is a stateless definition of an application requirement. So what do I mean by stateless? In ACI, we'll go back to this slide previously, the state of the network is not stored on the actual switches. So here we have a collection of, these are the spines and these are the leafs. So this is a classic leaf spine class architecture. The state of the network, the configurations are not stored on any of these devices. It is stored on the APIC controller. So the APIC controller is our source of truth. And then the APIC controller will then tell the network what to do. So we're going to define our network profile. So our web tier, our application tier, our database tier, any sort of layers 4 through 7 services such as firewalls, load balancers, IDS, IPS, whatever. We'll define stateful packet filtering in between, or stateless packet filtering in between, and how they need to connect and talk to each other. And we'll define that in the application network profile. So application tiers, connectivity policies, layer 4 through 7 services, and this is stored in either XML or JSON. XML is something we've been used to for a number of years. It's a structured data format, so rather than just a plain text file that has that's hard to parse, at least through scripting, XML is very easy to parse in scripting. JSON is the same way. It's a lighter weight structured data format than XML is, a little bit easier on the eyes, but both will work fine in ACI. So the concept is we're going to fully abstract this application profile. Again, going back to the application-centric nature of ACI, we're going to abstract it away from the infrastructure itself. Then we can apply that policy, and that policy will get instantiated onto the devices. So the APIC controller will tell the devices how to set up the network flows and so forth. IP addresses, all forwarding in the fabric is managed through the application network profile. IP addresses are fully portable anywhere within the fabric. So if we have a virtual machine over here, if we want to move it to a different location, so these virtual machines got moved. If we want to move them to a different location, then the IP addresses are fully portable. Even though that directly that these, and we'll get into this in a little bit more detail when we talk about how ACI works underneath the hood. But each of these leaves are not connected to each other through any layer 2 means, so it's all routed. But still, we have the ability to move IP addresses. So this IP address on this virtual machine can move from this leaf to this leaf, so we're not bound to a leaf. So virtual machines are free to vMotion throughout the fabric. Another advantage to doing but to do a centralized forwarding or centralized controller is that, for example, this leaf right here does not have any virtual machines that are this dark green here. So we don't have to program in any of the forwarding rules or ACLs or anything like that, or stand up any VXLAN VTAPs. We don't have to do any of that because it's not necessary. Think of it as like if you're familiar with the Nexus 7000, the TCAMs are if you have a VLAN that does not exist on a specific line card, that line card will not get any TCAM entries for that VLAN because it doesn't need it. Same thing with these leaves. They will not get forwarding entries. They will not get ACLs. They will not get any sort of network information on for a tenant or a virtual machine if that virtual machine does not exist on that leaf. So we can scale out TCAMs, ACLs, all that. We can scale that stuff out to a much higher degree than we could if we had to program every forwarding rule and every TCAM with every possible virtual machine or endpoint. Security and forwarding are fully decoupled from any physical or virtual network attributes. So we build security based on the application tier. So we have a web tier. So this VM and this VM might be part of that web tier. We're going to base the security rules on that web tier, on the connectivity between that web tier and the outside world, and that web tier onto the next tier that we're going to connect to. So we're not going to go into these individual switches and have to configure ACLs or anything like that. Those ACLs are going to follow these virtual machines. So we don't have to go in every individual device and configure the state. The state is kept on the APIC controller. It's defined in the application network profile. The application network profile is stored on the APIC controller, and then the APIC controller is responsible for configuring the devices on our behalf. So devices autonomously update the state of the network based on configured policy requirements. All right, so let's talk about the ACI fabric now. In ACI, we have two different types of switches. You are either an ACI spine or you're an ACI leaf. We also have the APIC cluster. This is the central point of truth, the central point of management for ACI. Typically, the APIC cluster is represented by 3 nodes. You can have as many as 5, and in some situations, such as a lab environment, you can have just 1. Everything from the servers to the layer 4 through 7 devices, such as firewalls and load balancers, to external L2 and L3 devices, connectivity, is all connected into the leaves. Everything else, nothing plugs into the spines except the leaves. We have one logical system to manage, and any IP address can exist anywhere on the fabric. In ACI, the spines, we typically will have 2 spines. You can have up to 6. 4 are typically shown in the diagrams just to disambiguate from the traditional pod architecture of a pair of like 7Ks and then 5Ks underneath that, and then 2Ks and fabric interconnects underneath that. So in ACI, typically it's 2, 4, or 6. Most of the time it's 2 spines. Then leaves can scale out to a much higher degree. So what problem are we solving with ACI? Doesn't make any sense to have a product unless you're going to solve a problem. So one of the issues that we see are overloaded network constructs. Typically, although it wasn't the original intent of the OSI model, typically we associate a single VLAN, a subnet to a single VLAN, and we use that as a segmentation method. For example, we'll have a DMZ VLAN, and we'll have a subnet or 2 on it. Our network policy is based on this large subnet, this large segment. Whether or not we're going to mark a packet, or are we going to permit it, are we going to deny it, redirect it, are we going to log our activities, our SLAs, what kind of QoS are we going to put on traffic in and out of a given subnet. And again, this typically is done on the subnet level, or it's done on the VLAN level. So these, and we're piling more and more endpoints such as virtual machines or physical hosts into these. And then, of course, layer 4 through 7 services, load balancers, firewalls, IPS, web application firewalls, SSL offload, etc. So we're all piling these into these different VLANs, these different subnets, these different segments. And then they're being used in ways that we originally didn't intend. We also have application language barriers. So in the network world, you see on the right, we speak the language of VLANs, of subnets, of protocols, and ports. Developers typically will speak in terms of application tiers. I've got my web tier, I've got my application tier, I've got my database tier, and I have providing and consuming those. So my application layer is providing a service, and my web layer is consuming that service. So developer and infrastructure teams need to translate between these disparate languages. So if you ask a developer what VLAN are you on, they're probably not going to know, and they don't care. But we care as network administrators. So when push comes to shove, when we need to diagnose an issue, we can run into some language barriers. Another issue we have is the complexity of a given setup. So a typical 3-tier web application, we're going to have web servers, application servers, and database servers. We're also going to have a number of layer 3 devices, layer 2 devices, firewalls, load balancers, VLANs, subnets, ACLs, etc. So just getting a couple of switches configured and a firewall configured can take a bit of work. The state of our network is not stored in any single place. It's stored in all of these different devices. So we have to go into switch 1, switch 2, switch 3, switch 4, firewall 1, firewall 2, load balancer 1, load balancer 2. Our policy is not kept in any place except our heads and maybe a Visio diagram perhaps. So we have all of these configurations here, and then let's say we're going to add a couple more web servers. So we go into our virtual machine, we spin up a couple of new web servers. Maybe we have to add in some new ESXi hosts, so we have to go into a switch, figure out what switch that ESXi host is configured on. We need to add new VLANs to that to those new switch ports, typically we've been doing this by hand. Also on the load balancer side, we go in by hand and we configure the load balancer to add these new web servers into the VIP. So it gets quite complicated. It's a process done by hand typically, and it's prone to error. In fact, if you think about it, when do we make a lot of these changes? Well, we make them at night under cover of darkness because we have a low confidence of success. We know that this is an error-prone methodology, so we do it at night where if we make a mistake and take down the network, we've got time to fix it and we're not going to disturb as many users. So we have a low confidence of success and a high cost of failure. Because we're not segmenting our applications, because we're not doing any sort of multi-tenancy, if we make a mistake, we can affect all of our applications and not just a few of them or not just one of them. So what is an application to the network? It's more than just a VM or server. From the networking perspective, we tend to think of IP addresses, we tend to think of subnets and of VLANs, but that's not what an application is. An application is a collection of endpoints, plus all the layer 2 through 7 network policies that we have in between these endpoints. These endpoints are typically VMs. They can also be physical hosts. They could be containers now. So we need to group them together in some way. Typically, we throw them all of our web servers, we throw it on a given VLAN. All of our application servers, we throw it on another VLAN. And we mix all of our applications together. So application number 1 is going to share the same, its web tier is going to share the same VLAN as application number 2, and typically that's what we might refer to as a DMZ VLAN. We also have to keep into account the relationship between these tiers. In traditional networking, it's blacklist networking, so everything is allowed to talk to each other unless we explicitly deny it. So we put things like firewalls in place. Well, firewall rules are based on networks and not applications. So how many of you have ever dealt with firewall rules that shrink over time? Typically, that's not how it works. Typically, we're growing our firewall rules, and we're very hesitant to remove firewall rules from a given firewall because we're not sure if it's going to disrupt anything else. Even the most carefully annotated firewall rule set is going to probably have some mistakes in it in terms of the annotation. So if we take out, let's say we have a comment that says the next 5 rules are for application X. And then we get a call from the application X developer saying we've retired the application, which, I mean, let's be honest, how often does that actually ever happen? But let's say in some miracle it did. They call us up, they say application X has been retired, you can pull out the firewall rules. So what is your confidence if you go into a firewall? And this could be from any vendor. This could be Cisco, this could be Palo Alto, this could be Checkpoint. What's your confidence that removing those rules are actually not going to affect anything else? And then most of the time we will protect from the outside world. So we'll put a firewall in between the outside world and our first tier, our DMZ. So our web servers and the outside world will have some protection in there. And then it's kind of a free-for-all internally because we can't really because we don't want to scale out our firewalls. We'll have to add a ton of more firewalls to put them in between our different application tiers. So for example, right here and here. So typically we'll put a firewall in here. And then somewhere in here, it's just a free-for-all. So web servers can talk to the application servers without any restriction. App servers talk to the database servers without any restriction, which is not a great security profile. So teamwork. So let's create a logical model to support the app. Our logical model is we're going to have a collection of endpoints, web servers, a collection of endpoints that represent the application servers, and a collection of endpoints that represent the database servers. Then we can insert services, firewalls, load balancers, IDS, IPS. We define these policies. We put them, the way that web servers and application servers talk to each other is through consuming and providing contracts. So that contract will have things like you can allow port 8080 through to the application server, and on the database server, we're going to allow connections from the app servers to the database server on 3306, which is the typical SQL port. We define all of these in the APIC controller. So we're not going into every individual switch. We're not creating the policy in our brains and then going to every individual switch and applying that policy. We're defining the policy onto the APIC controller. So we're defining endpoint groups, we're defining service nodes, and putting them into the APIC, and then the APIC, and then we define the contracts and how they talk to each other, and then we're putting that into the APIC. Then when we go to deploy, all these things get configured all at the same time, and then they go right into the ACI fabric. We can also take this definition. So what you're looking at on the left here is we've got our outside EPG. So this is when we consider this the internet. We've got our contracts and services. So what are we going to allow to connect from the outside world into our web tier? What devices do we want to insert? What sort of service chaining do we want to put in place? We do want to do firewall, of course, SSL and load balancers. Okay, we'll do that. We're only going to let ports 80 and 443 through. So we define that. Here's our web servers. So these are the endpoints. Web server number 1, web server number 2, web server number 3. And if we want to add more web servers, we just put them into that endpoint group. We don't have to make any other configuration changes. So things like the policies for the ports are going to follow the endpoint group rather than have to configure individual IPs. So our web servers to our application servers, we can throw in a firewall, or we can use the built-in ability for packet filtering in the ACI fabric. So we're going to let port 8081 through. We might use a load balancer as well. So the web servers can hit a VIP, and the VIP will spread the load in between the different application tiers. And then from the application service to the database tier, we could put in some packet filtering or an appliance firewall, maybe a load balancer, although databases typically don't use load balancers. And of course, we're going to let through only the appropriate port, in this case 1443. We can take this, we'll call this an application network profile. So that's the encapsulation of all of these, of all of this policy for a given application. And we can copy it, or we can template it and make it reusable, so that our dev environment can look exactly like our test environment, can look exactly like our production environment. The difference is you can see here we're putting in more web servers, more devices inside of these endpoint groups. So the logical model overview. If any of you are familiar with Cisco UCS, one of the defining characteristics of UCS is the concept of stateless computing. So what does that mean? Well, the state of a server, so state being things like boot targets, MAC addresses, worldwide names for fiber channel adapters, VLAN configurations for the ports, and vSAN configurations, even firmware on the motherboard, firmware on the NIC cards, etc. All that is kept off of the servers. It's stored inside of UCS Manager. We take all of that together. What we define as a server, we call it a service profile. So back in the day, when I was a system administrator, we used to give servers kind of cute names, like we'd name them after Simpsons characters or Greek gods. So we might have a couple of servers. We might have Apollo, and we might have Jupiter, or name them after planets like Jupiter, Saturn, etc. So in Cisco UCS, Jupiter, instead of being a physical server, is now a service profile. And then we apply Jupiter to a given compute node. That compute node will then take on Jupiter's attributes, will take on its MAC addresses, worldwide names, boot targets. It'll get its firmware up or downgraded to whatever firmware we want Jupiter to have. And then we can, and then that server will exist there. If we need to move to a different compute node, it's just a simple migration. So we're taking that same concept and we're applying it to networking. And it's not any coincidence that the same people that developed Cisco UCS also developed Cisco ACI. So we're going to take the concept of stateless networking. We're going to remove the state off of the physical nodes, off of the physical compute or physical network devices. Because if you think about it, our forwarding policy, our network policy, is not stored on any one switch. It's distributed throughout the switches. It's VLAN configurations, SVIs, routing profiles, and routing protocol configurations done through dozens of switches potentially. And it's not stored in any single place. It's just little pieces of it here and there, and it's hard to reproduce. So in ACI, we're going to take the concept of, we're going to take that entire forwarding policy, and rather than base that forwarding policy on a network, we're going to base it on an application. Because if you think about it, that's why we're here. The entire reason our network exists is to support applications. So let's build a logical model, not on the network, but on the applications that reside it. And then that logical model will translate between what the application knows and what's going to go on the network. So we encapsulate all of that policy for a given application into an application network profile. And that, again, that policy is, the endpoint groups. So these are the collection of endpoints for a given tier for an application. Again, we're using the common 3-tier example here: web server, application servers, database servers. It doesn't necessarily mean your app's going to look like that. Many apps may have a collapsed tier architecture where we have the web and app servers on the same systems, and then we just have a separate database layer. But either way, this is a pretty good example, a pretty good place to start. The way that for example, this might represent the internet. The way the internet communicates with the web tier is we use contracts. Define the communication between different endpoint groups. Stateless filtering between EPGs is implicitly provided by the ACI fabric and may be able to eliminate the need for some firewalls within a data center. One of the challenges that we have with security is that, like I said before, our security model is typically everything can talk to anything unless we explicitly deny it, or unless we put a device in place. From the outside world to our first layer, our web servers typically, we're going to have a firewall. Typically, most places do. But internally, between maybe our web layer and our application layer and a database layer, we're not going to have a firewall in there a lot of times. So what we can do is we can put in some ACLs. Now, we can do this in traditional networking, but it doesn't really scale very well. Our VMs are migrating from one location to another. We're going to start eating up TCAM space. If we pile in a ton of, virtual machines can number in the thousands or even 10,000s for a given data center. So we're going to really start eating up TCAM space if we put it in every switch in our network. So it's just not really a scalable, a workable solution if we're doing things by hand. But in ACI, we define all that policy into our application network profile. And then the deployment of that ANP, the application network profile, onto given hardware is done in an automated way. And then it will apply those ACLs to specific leaves that actually need that. If we have a VM we have a tenant that's not on a given leaf, it's not going to get any of those TCAM entries. So terms, very important terms in ACI. Over and over again, we're going to talk about endpoint groups. Endpoint groups are a container for objects requiring the same policy treatment, such as app tiers or services. Now, when we say container, we're not talking about like Linux containers. We're talking about a conceptual container, a conceptual place to put things. So most of the time today, we're going to define an EPG as a VLAN, but we also have the ability to define an EPG by IP address if we have the right equipment. Another one is a tenant. Most of our network configurations are single tenant, or if it's multi-tenant, most networks can support multi-tenancy, but the network itself is not multi-tenant. We're using some other multi-tenancy methodology on top of a given network. But in ACI, we do have the concept of multi-tenancy. You can put Coke and Pepsi onto an ACI, so we can have an ACI tenant Coke, we can have an ACI tenant Pepsi. We don't have to do it with competing companies. We can do it with different business units. We can do different developer groups. We can even do different individuals. So it's a logical separator. It separates traffic, admin, visibility. It also lets us shrink the failure domain. So we can create a tenant and hand more of the control over to the consumer. So part of the DevOps model is that the developers are in operations. The lines are blurred between who does what. So we can give the developers the ability to spin up networks, to spin up EPGs, to spin up VLANs, etc. Or not really VLANs, but to spin up an EPG, which becomes a VLAN. We can let them spin it up and give them the keys so they don't have to open up tickets. It goes back to the concept of cloud computing, and one of the core tenets of cloud computing is the ability to do self-service. So a multi-tenant model allows us to restrict the damage that they can do in case they make a mistake. If they make a mistake, if Coke makes a mistake, it's not going to affect Pepsi. We have private L3 networks equivalent to a VRF. We call these contexts in ACI, but it works the same as a VRF. This is a separate routing space, routing instance, and we can use them for administration separation. For example, if I have Coke and Pepsi as tenants, the Pepsi might have Pepsi, Diet Pepsi, Mountain Dew as different contexts inside of that tenancy. Bridge domain. A bridge domain is not a VLAN. This is one of the common misconceptions of ACI. A bridge domain is not a VLAN. It's simply a container for one or more subnets. We can use it to define a layer 2 boundary, but typically it's a collection of layer 2 boundaries, which we call endpoint groups. Contracts represent policies between endpoint groups. Contracts are provided by one EPG and consumed by another. We can see that those relationships either on a CLI, an API, or a graphical interface. So let's take another look at these different objects that we just defined. So at the top of the model here, we have a tenant. So this could be Coke and Pepsi, or it could be John and Jane. Above the tenancy, we have the entire system. So this might be the infrastructure. We call it the universe, or uni. And then below that, we'll have multiple tenants. Inside of a given tenant, we can have connections to various layer 2 and layer 3 outside networks. One of the interesting aspects about ACI is VLANs. VLANs are locally significant to a tenant, and we can actually have overlapping VLANs even within inside of a tenant. So our connectivity to the outside world can scale beyond just 4,000 VLANs. Application network profiles. So we can have multiple layer 2 or layer 3 connections. We can do layer 3 peering through routing protocols, IGPs, such as OSPF, EIGRP is supported, IBGP is supported, and if you like to live dangerously, you can do static routes. And we can also connect to traditional layer 2 devices. So while there is interesting stuff going on inside of the ACI fabric, ACI connects to the outside world via traditional layer 2 or layer 3 forwarding. We also have application network profiles. We'll typically have many of these, application 1, application 2. Application profiles have a collection of EPGs, one or more EPGs per application profile. However, an EPG cannot exist in more than one application profile. So one EP, we can have multiple EPGs in an ANP, but an EPG cannot exist in more than one ANP. We also have the concept of bridge domains. A bridge domain can have one or more subnets in it. Typically, we'll have one, but you might have more than one. EPGs can only exist inside of a single bridge domain. And then a bridge domain can only exist inside of a given VRF, a given context. Bridge domain, you can have multiple bridge domains. Typically, you'll have one, maybe two. One might be like your DMZ bridge domain, and another one might be in an internal private routed space. We also have the concept of contracts. EPGs talk to each other through contracts. If you do not have an EPG for or if you don't have a contract for an EPG, that EPG cannot talk to anything, and nothing can talk to that EPG. So we are whitelist networking. So you have to explicitly allow traffic in or out. All of the traffic inside of an EPG by default can talk to each other, but there's ways to restrict that even. And then a contract is a collection of subjects, and a subject is a collection of filters. And filters is something like TCP port 80 or UDP port 53. So we can have multiple filters inside of a given subject, and we can have multiple subjects inside of a given contract, and we can have multiple contracts for every EPG. An application network profile, we have the concepts, again, the concept of the outside world. Typically, we'll call this an L3 out or an outside EPG, which represents a layer 3 network. A lot of the times that will be the subnet of 0/0. So that means everything. To get the outside world into our web layer, we have to provide a contract. So the web EPG is providing, and the public outside EPG is consuming this web contract. And this web contract might say, let's let port 80 through or port 443. The web servers exist on a bridge domain, and the bridge domain has a subnet on it. And those subnets exist on a single layer 3 context. From our web layer to our application layer, we're going to have another contract. So this is Java, so maybe this is port 8080. So we're going to provide this contract to the web layer. So the web layer will be able to make connections to our app layer on port 8080. Same thing with our database layer. Our database layer is running SQL. 3306 perhaps is the port that we're using to provide our SQL services. We're going to provide that contract, and the application tier is going to consume that project. Now, one of the things you'll notice is that the arrow is pointing in the opposite direction of the traffic flow. So the traffic is initiated from the application tier and destined for the database tier. However, because of the provider-consumer construct, the contract inbound on port 3306, kind of hard to read my writing here, is provided as a contract. So we're providing that, and so the arrow is pointed that way. So that's the logical model. Now let's talk about the concrete overview. So we're applying our policy to the endpoints. We define our policy. We put the ANP, the application network profile, into the APIC. And then the APIC goes and implements that into the various configuration, into the various nodes. So for example, we'll have a VM. It's going to attach to the fabric. So typically what will happen is that a VM will get associated to, if it's VMware, it's going to get associated to a port group. That port group is going to be assigned to VLAN. That VLAN is going to be assigned to that DVS, the distributed virtual switch, and connected up into a leaf. That VLAN is going to be associated with endpoint groups, so that if we put more than one VM, any VM that we put inside of this port group is going to be put inside of a VLAN. It's going to end up in this EPG. When that EPG is, when that endpoint is detected, it gets instantiated into the policy onto that leaf. So whatever forwarding rules that we need to put in place, whatever ACLs, all that gets put into the TCAM space of that particular leaf. Now, this leaf right here doesn't have that EPG, doesn't have that tenant, so it's not going to get any of those updates into its TCAM, so we can scale out our TCAM space much more efficiently. So whenever we make whenever we make a change to the logical model, the APIC controller takes that change and then makes a call into the APIC fabric into a given node. The logical model locally gets changed, the subset of that logical model gets changed, and then we do an update to the local NXOS processes, and then that gets pushed into the actual network chips. So that's how we do the concrete model, that's how we do the logical model, and that is an overview of Cisco ACI.